Okay, now we're going to move on to geometric series. And the key thing about geometric series is it's about multiplying. So, what can we see here? Say we've got 2, 6, 18. Well, you might be able to see that what we're doing is multiplying by 3 each time. And I mentioned this in the previous video, but we have a first term and we have a common ratio for this one. So the common ratio is going to be what you multiply each time to go between the terms. So in this example, we've got that A is 2 and R is 3. And we're going to, the first part of this video is we're going to try and do exactly the same thing. We're going to try and come up with an nth term, and we're going to try and come up with a formula for the sum of the first n terms. So A, the first term, is 2. A2, the second term, is going to be 2 times 3. So this is A1 is equal to just A. A2 is equal to AR. A times R. A3 is going to be 2 times 3 times 3. Well, that's going to be 3 squared. So A2 is going to be A3 is going to be AR squared. And now you can see that the number here and the number here are 1 apart. It's again similar to the previous time. You could see this as AR to the 1, you could see this as AR to the 0, and this pattern continues. So what would we have if we had AN? Well, we would have 2 times 3 to the power of 1 fewer than that, n minus 1, and we get the nth term formula, which is AR to the n minus 1. This is the nth term of a geometric series, and that's going to be very important soon. Okay, we also have a formula for the sum of a geometric series, and this is in the formula book. And it is like this. Now, it looks a little bit ugly on first glance, but actually the proof is relatively similar to the previous one for arithmetic, in that you kind of create 2 copies of it and then kind of mash them together in some way to help us. So here is the proof. Sn is equal to A plus AR plus AR squared plus ... plus the last term is AR to the n minus 1, and the previous to last term is AR to the n minus 2, one before that. And what we're going to do is we're going to subtract R times this whole thing. So what I'm going to do is I'm going to see that if I multiply A by R, I get AR, and I'm actually going to write it there. So this is multiplying A by R, and I get that. If I multiply AR by R, and I'm going to written a slightly wrong thing there. So if I multiply AR by R, then I get AR squared. If I multiply AR squared, I get AR cubed. That's going to go in there. Remember, there's an AR cubed in here. ... Multiply everything by R. Everything jumps up by 1 ... Everything jumps up by 1 space. So that one's going, that we can't see, is going to, sorry, this is a minus. We're going to get ... minus AR to the n minus 2. AR to the n minus 2 multiplied by R is going to be AR to the n minus 1. AR to the n minus 1 multiplied by R is going to be AR. So we can see that everything multiplied by R jumps along 1 space. And so now when you do this subtraction, everything cancels. So what have I got? I've got Sn minus R times Sn is equal to A cancels, 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 minus AR. Well, let's shuffle that along. Minus AR. That's all we're left with. And now you can see how we might be able to get this proof to work. So I'm going to factorise out Sn from this side. I get Sn, open brackets, 1 minus r. And I'm going to factorise out ar to the n. I'm going to go back, ar to the n here. So I have actually got ar to the n here. So I'm going to factorise out a. So I get a, open brackets, 1 minus r to the n. And I'm going to divide both sides by 1 minus r to get Sn is equal to a, open brackets, 1 minus r to the n, all over 1 minus r, which is as we got here. Now, what about this other version of the formula? Well, actually, you can get to that by multiplying top and bottom of this equation by minus 1. And it turns out it's just another version of the formula, which is useful. R to the n minus 1 over r minus 1. In particular, if r is a number between minus 1 and 1, this is more useful because you get a positive value here. And if it's a number that is greater than 1, this is more useful because you get a big number here, and that just kind of makes things kind of more useful if we're in that situation. And that's the proof of that. And you would be expected to prove that even though the formulas are in the formula book. So it's one to remember. Just remember the pattern. Okay, so let's do a quick example. So the first term of a geometric sequence is 3 and the fourth term is 24. So straight away, I'm going to write down that a is equal to 3 and I want to know what r is, but I don't know yet. So I'm going to write down the first couple of terms and see what happens. I get 3. Then I get something I don't know. That's the first term. So I've got the first term, second term, third term, and the fourth term. And I can see that I don't know what the second and third term is, but I do know this one is 24. So I can see that if I multiply by r, I get that. If I multiply by r, I get that. And if I multiply by r again, I get 24. So I can see that 3 multiplied by r 3 times, r cubed, is equal to 24. So r cubed is equal to 8, and we discover that r is 2. Now let's just check that. 3 times 2 is going to be 6. 6 times 2 is 12, and 12 times 2 is 24, so it works out, and that is our value of r. So if I need the 7th term, I'm going to remember that the 7th term, well, let's write down the formula for the nth term, which you do need to remember, it's not in the formula book, is ar to the n minus 1. So the 7th term is going to be a, which is 3, multiplied by 2 to the power of 7 minus 1. So if I was to do this in my calculator, 3 times 2 to the power of 7 minus 1, well 6, and I get 192, which is the 7th term. Okay, so now I want to find the sum of the first 7 terms. So I remember that my sum formula is a, open brackets, r to the n minus 1 over r minus 1. I've chosen this version because r is bigger than 1, so it's going to make the bottom positive. So this is 3, open brackets, the r value is 2 to the power of, what I'm saying is I'm calculating S7. S7 is equal to 2, the first term is 3, open brackets, 2 to the power of 7, minus 1 over 2 minus 1. The bottoms become very easy to work with, but let's do this properly. So, the bottom's just going to become 1, so 3, open brackets, 2 to the power of 7, minus 1, close brackets, and I can see that the sum of my first 7 terms is going to be 381. And that is that example. So we can see how that works. Okay, another quick example. The first term of a geometric sequence is 2, and the third term is 8. Now actually the question wouldn't be written like this. Something is wrong, but I want you to see where it is in it. So A is equal to 2, and we have got the sequence 2 question mark 8, where we are multiplying by r and multiplying by r. So this gives me 2r squared is equal to 8, r squared is equal to 4, and r is equal to, well, you might have been able to see it and think that this middle term was going to be 4, but r can actually be plus or minus 2, and that's really important to spot this. Actually, this is plus or minus 4, because if r was minus 2, it would be 2 times minus 2 is minus 4 times minus 2, it would still be 8. So actually, we could have plus or minus 16 as the fourth term. So really, this question said, find the possibilities for the fourth term, because there are 2. Something to be careful and watch out for. I know that square rooting plus or minuses is a common mistake. Okay, something a bit harder, and you might think this question looks a bit like something we did in the previous video, and it does, but we need a slightly different strategy for geometric series. We can see this is geometric because we are multiplying by 2. So A is 5 and R is 2, and I want Sn to be bigger than 1 million. And what is the smallest value of n such that that will happen? Okay, so what we're going to do is I'm going to put the formula in. So it is A, and we have got r, so I'm going to do r to the n minus 1 over r minus 1, and I want that to be greater than 1 million. Geometric series grow very quickly, so that's why we're seeing all these big numbers all of a sudden. So this is 5, open brackets, 2 to the n minus 1 over 2 minus 1 is greater than 1 million. So that is 5, open brackets, 2 to the n minus 1 is greater than 1 million. 2 minus 1 is just 1. Divide both sides by 5. I get 2 to the n minus 1 is greater than, and here we're going to get 200,000. So 2 to the n minus 1, 2 to the n has to be greater than 199,999. Oh no, sorry, adding 1. So it is 200,001. And at this point, we need to find what something in the power is. So you might think logarithms. And that's what you should learn to think. When you're looking for something that's in the power, you want to think logarithms. So that's what I want you to be thinking. And I'm going to find the critical value. So I'm going to solve 2 to the n equals to 200,000. And I'm going to do that by this method. So I want to do log base 2. What power of 2 gives me 200,001? And the answer is 17.6. So critical value is n is, and I'm going to check what we get, 17.6. Yeah. And so we can see that since this is growing, and when does it first exceed 1 million, we can see that we need to go up 1, and so n is equal to 18 is going to be the first time that this sequence exceeds 1 million. Okay, and we can check this. So if I was to do the sum of the first 17 terms, I should get that it is less than it. So let's do the formula. So 5, open brackets, 2 to the power of 17. That should not be big enough, over 1. And indeed it is too small. And if I go back and change this to an 18, it is over 1 million, so we are correct. And that's a slightly harder example for you to have a go at on these kinds of questions. And you'll see some of these in this exercise. So I recommend that you have a go at these questions. I'll make that slightly bigger. From exercise 3C and 3D. I've kind of covered a few things that should help you have a go at those questions. I am, however, going to do one more part in this video, something called the sum to infinity. This kind of goes with the geometric series, and so it's really good to kind of do it now, because then we would have covered arithmetic and geometric all here. So I would say have a go at these questions now, and then kind of come back to this point in the video and carry it on. So I'm going to go on to the sum to infinity. Okay, so say we had this. 1 plus a half plus a quarter. Well, we can see these numbers are getting smaller and smaller and smaller. And indeed they do. They get smaller and smaller and smaller and smaller. And even though you're adding up an infinite number of terms, they actually converge to the sum. Adding them all up converges to a value. And I can show you why that is with a picture. Say that I had this box. And what I'm going to do is I'm going to say this box is too wide. So here's 0, think of it as a number line, here's 1, and here's 2. Well, firstly, I'm going to add 1. So that is going to take me up to here. So that's me adding 1. So that's the 1 done. Then I'm going to add a half. Well, that's going to take me up to here. That's the half done. Then I'm going to add a quarter. Well, that's going to take me up to 1 3/4. That's going to be that bit. So that's that done. The next bit would be an 1/8. That is going to be this part. The next bit would be a 16th. The next bit would be a 32. And actually, what happens is, as I keep adding up, it's never going to go past 2. In fact, it's going to get closer and closer and closer to 2. And if you, and this is a kind of a weird thought, but if you add to infinity and you add them all up, mathematically, it actually is 2. And it is exactly equal to 2. And the reason for that is that if we look at the formula here, Sn is equal to A, open brackets, 1 minus r to the n, divided by 1 minus r. If r, in this case, so for this sequence, we have that A is 1 and r is a half. If r was a half, this equation becomes this. So if r is equal to a half, we get A, open brackets, 1 minus a half to the power of n, divided by 1 minus a half. Well, if you look at this term here, and I think this is the important term, if you look at this term here, as n gets bigger and bigger and bigger and tends to infinity, a half to the power of n, well, that you get a half times a half times a half times a half times a half. This actually approaches 0. So S infinity, if you add up an infinite number of times, we actually get A 1 minus 0 over 1 minus a half. Well, in this case, actually A is 1. So this becomes 0. So this is 1 over a half, which is equal to 2. And that shows why we got 2 from above. So in general, this only works when this number, when r here is between minus 1 and 1, because otherwise that number gets bigger and bigger and bigger. If it's between minus 1 and 1, that gets smaller and smaller and smaller. So in general, for r between -1 and 1, can't be 1 or -1, it has to be between, S infinity is equal to A 1 minus 0, because that bit tends to 0, over 1 minus r, which is equal to A over 1 minus r. So you can just calculate it straight away. And this is in the formula book. This is in the formula book, the sum to infinity of a geometric series. Takes a little bit of time to get your head around, but just like listen through what I just said, read through the textbook, see if you can get a good idea of it. Okay, we're going to have a look at this geometric series. Find the sum to infinity of this geometric series. Again, we can see that A is 3 and R, crucially, is between -1 and 1. So it converges. Converges means that it's going to come to a value. Diverges would be the opposite. So if R is less than -1 or R is greater than 1, then it diverges. And if we've got A is 3 and R is a third, we can say that S infinity is equal to, well, we know the formula is A over 1 minus R, which is 3 over 1 minus a third, which is 3 over 2 thirds, which is equal to 9 over 2. And if you test it and keep adding that up, you'll see that it gets closer and closer to 4.5. You can try it on a calculator to see that it would be the case. Okay, another quick example. Say we've got a geometric series with A equals 5 and S, the sum to infinity is 20 over 3. Find R. It's just simply a case of using the formula S infinity equals A over 1 minus R. So 20 over 3 is equal to 5 over 1 minus R. Multiply, multiply. 20 1 minus R is equal to 15. 1 minus R is equal to 3 over 4. I'll just double check my thing. Yeah, okay. And so 1 minus 3/4 is equal to R. And so we get R is equal to 1/4. Okay, just check my working. Yeah, okay, I'm happy with that. So there we go, R is 1 over 4. Okay, have a go at some of the questions from that exercise. It's also going to exercise 3E. It's also going to revise some of the other things that you've been working on as well. So it should be kind of a good practice of that as well. Page 75, if that is useful to you. And next video, I'm going to move on to sigma notation and recurrence relations, and also do a quick summary of everything we've seen as well. Okay, thank you very much.